Hi everyone, welcome to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Steve Sun, who is an associate professor at Columbia University since 2014. He obtained his PhD from Northwestern in 2011 and worked as a senior member of technical staff at Sandia National Lab from 2011 and 2013. It was actually across the street from Lawrence Livermore National Lab, so it was very close. And his research focuses on theoretical, computational, and data-driven mechanics for multi-phase materials with complex microstructures. He is the recipient of several awards, including the IACM John Agris Award, ICE Gienkiewicz Medal Prize, the ASCE EMI Da Vinci Award, the NSF Career Award, the Young Investigator Award from the Army Research Office and Air Force Office of Scientific Research. Okay, today Steve will talk about data-driven constitutive updates from model-free poroelasticity to level set plasticity trained by neural networks, which is very interesting topic. So please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Steve by asking one random question as usual. Today's random question is, what is your favorite things to do other than research?
Other than research? Yeah, I would say spend time with my children. I think.
Student?
Spending time? My children.
Your children.
Well, in a sense of my student is also my academic children, but if I have time, I will spend time with my biological children.
How many do you have?
I have two, so.
Oh, you have two? Okay, so you have a plenty. All right, the stage is yours. Thank you, Steve.
Okay, so yeah, so Yanso, thank you very much for the introductions and the invitations to give the talk. It brings back my memory. The time I live at Livermore was a wonderful memory. So today I would like to talk about our recent work related to using machine learning or data-driven techniques to create constitutive response for computer simulations, in particular for porous media and for solid that actually have a path dependence constitutive response. Okay, so before I get into the details, I would like to first give the credit to the hero who actually done the majority of the work and all of the implementations. Nicholas Venice, my former student and my current postdoc that work on the level set plasticity, and Bahadur Baminic that are actually working on the model-free pore mechanics. So roughly speaking, I will talk about the model-free pore mechanics in the first half of the talk, and I will talk about the level set plasticity. So before I get into the details, I would like to talk a little bit about the history of the rather unconventional way to write constitutive law, which is something that which is actually related to the AI and machine learning. So we did a literature review. I think that we can actually at least trace back the first neural network constitutive law to in the 1988 where we know that there's a attempt on training neural network to create a constitutive law for concrete. By that time, there are not yet any recurrent neural network yet, so the approach is to include multiple previous time steps and then using it to actually represent a path-dependent behavior. Then there are more work related to the deal with the various improvement on the neural network constitutive model. But in 2016, actually, the first author is in the audience. Then there is also another approach on introducing model-free approach that enable a computer simulation to be done with our constitutive law. And then there are many other work that are actually related also to the so-called deep data revolutions. And then, I guess a little bit of personal history. I think that when I was a PhD student or postdoc, we are still not yet in the AI spring, so-called. So I also try to ride the tide of the data resolutions and then learn. I graduated in 2011, so a little bit before that. And so, so the talk I'm going to talk about, in a sense, is a summary of my own perspective on, or based on my own experience on working in trying to using the machine learning AI technique to generate a constitutive law. So I will first talk a little bit about the different approach, maybe a little bit of survey on the difficult, on the various approach that we can find in the literature. And then one thing that we actually want to achieve in using the AI and machine learning to create constitutive law is that we want something very easy to interpret, but we also want something that works well with the limit data. So in a sense, we can, in the literature, we can find neural networks that are only used for material parameter identifications. In this sense, the model will be very easy to interpret because it's with the algorithm and with the theory is really easy to interpret given constitutive model. But then the problem is that it lacks the ability to discover new mechanism. And then there are symbolic regressions and recurrent neural network that actually have different attributes. Symbolic regression, for example, can actually allow us to create mathematical equations based on the data, but it's really hard to use in high dimensions simply because the parametric space is so large. There's so many ways to write the equations. And then there are recurrent neural networks that are actually hard to interpret the results, at least not directly. And then there are model-free approach that doesn't have a model at all, but it requires a large amount of the data. So how do we get there is something that I initially think about. So how do we actually write a model that doesn't require a large amount of data and yet being able to capture the physics? But then there are another thing that are important to consider, and that is when we have a very complicated physical phenomena, and then it's really hard to write a model. So when we train a constitutive law, it involves a large amount of computational power, maybe produce a lot of greenhouse gas along the way. But also training a constitutive law or creating a constitutive law is not easy. In this case, in the recurrent neural network, for example, we need to, in addition to formulating the problem, we also need to tune the hyperparameter. On the other hand, the model-free approach has a great advantage in the sense that if we have enough data, so we don't actually need to spend any time on creating a model. We just need to actually create a mechanism to search for the material data, and so there's no VMV. So what in this talk, what we actually want to focus on is actually two situations. One situation is that we have enough data, and then in this case we can actually adequately using a model-free approach to actually complete the computer simulations. or when we actually have a model, or we actually gathering the data, in which case a deterministic model are actually insufficient or very difficult to capture the physics. This is actually commonly encountered in, for example, in hydraulic simulations where the permeability porosity relationship has very high invariance, in which case the point of writing a deterministic model that captures the mean behavior is less meaningful because you simply cannot matching the experimental observations. Another case we need to deal with is that in general, unlike the other field where the big data assumptions is actually can be taken for granted, experimental data for solid or for hydraulic data are usually expensive. So when the data is actually limited, the model-free approach, because of the lack of the model, may not actually functions as good as we would hope to be. In this case, we want to switch to a machine learning model that actually allow us to predict the future events without a loss of data, without demanding a loss of data. And then what we actually also want to explore is the interplay between the two. Is it possible that we can mix this these two strategies to create the best computer simulations? Depends on what data we can get. And this is actually a problem that we constantly thinking in our research group. So roughly speaking, the model, the machine learning model are done by my postdoc, Nicholas Venus, and then the model-free approach are actually done by Bahadur, who's in the audience. So here we basically extend the idea that appears from an influential paper from the Caltech group. We basically trying to solve we have a computer simulations that are governed by the balance principle. For the pore mechanics problem, we have the balance of linear momentum, and we have a balance of mass that actually function as the physical constraint. Okay, so in these two problems, there are two constitutive laws that are actually require experimental data to complete the model. One is actually the relationship between the strain and the effective stress. Another one is actually the relationship between the pressure gradient and the Darcy's velocity. So if you look at the data pair, we actually have a strain stress pair, and then we have a pressure gradient and velocity pair. And in a typical way, when we actually want to create a pore elasticity model, we would actually conduct tests to obtain the stress-strain relationships with under different pore pressure, and we would actually try to conduct hydraulic tests to obtain the relationship between pressure gradient and velocity. Now here, one thing to notice is that in general, the solid mechanics and the hydraulic data have different level of variance. You can see that, for example, in this digital rock physics paper that published in 2013, the Buck modulus discrepancy are actually within 10 to 20 order, but the hydraulic constitutive response are actually within 1 order in the log scale. So so the data inherently have different amount of variance or noise, and so the treatment to combine these two constitutive laws together is actually not a trivial task, in particular in the model-free approach. So here we did not actually did anything new compared to the classical model-free approach. The only difference is that we actually add additional constitutive law and new governing equations. So long story short, the idea is that we would actually have a solution space that are actually sorry about the moving of the slide. So we would actually have a manifold that actually collect all the admissible solutions from the physical constraint, and we actually also have a material manifold that are coming from the data. The key point, unlike the classical problem, is actually not to create a smooth constitutive law that actually allow us to put the two models together to yield a unique solutions. But we want to actually find out what is the closest point in the material database that actually minimize the distance of the physical constraint. So in this case, this would involve optimizations that are both continuous in the sense we want to actually find out the way to minimizing the distance from the manifold of the physical constraint, but we also need to select the particular material point in the database that allow us to minimize the discrepancy. So the extensions of the porous media problem is actually is not particularly difficult. What we actually need to do is actually to minimize the discrepancy between the material point data and also the constitutive law. So here, the important thing that we need to invent here, however, is the notions of the distance. And this we will talk about it later on. But long story short, in the single physics case, what we actually want to introduce is actually a norm for a product norm for the strain and the stress space. We want to introduce the notions so that we can measure how close the stress strain data from the material data are actually to from the point of the constitutive manifold. Okay, so here the idea is to use the product norm in the sense that we would define a vector space. We will consider the coefficients of we will consider the component of the strain and stress as a 6-dimensional component. So together, the stress strain would have 12 would constitute a 12-dimensional vector space and equipped with a norm that actually resemble an energy norm. So S and C are actually so S here, the S tensor here is actually the inverse of the C tensor. So in this case, this provides us a measure of the distance between the constitutive data, and we can expand that idea into the pole mechanics data as well. So in the case of the multiphysics, we would actually solve the minimization problem for the solid and also for the fluid. But then the questions that we need to ask is that how do we define this C and then the S, C, and also these two norm? Okay, so you can see that the strain and stress are actually of different order. They have different units, so it makes sense to actually rescaling them to make the notion of the distance actually more clear. But then the thing is that the constitutive response are not necessarily linear. So if we actually introduce a product norm to actually measure the distance, is it the best way? So this is something that we are currently investigating. Sorry, I think some problem with the. Okay. So the problem, the optimization problem, including 2 steps. And the interesting thing is that one of them is actually continuous. We want to actually fix the material data point that we idealize, and we actually want to find the physical field such that it minimizes the discrepancy of the data and the physics field and then this could be differentiable optimizations because the residual are actually smooth. But on the other hand, we also have a local step. This is actually, in a sense, the replacement of the constitutive law. We actually want to identify the material point that actually on the database that are actually minimizing the distance. In this approach, in the model-free approach, the most difficult part or one of the most major challenge is to solve the discrete optimization problem, where we don't rely on the gradient, but rely on the search and ranking to determine which point is actually the best well-fit, the optimum point to actually fulfill the closest to the physical constraint. Okay, so the continuous problem are actually, the manifold are simply the specific a constitutive response that fulfill the balance equations for the linear momentum and the mass. So in this case, we can actually introduce we can use the Lagrange multiplier approach to enforce the particular data set to actually formulate the optimization problem. This is actually very similar to the original data-driven paper. The only thing that we add again is the new additional equation for the balance of linear momentum and then the introduction of the time. So, but then the thing that we want to address is the following. As we see earlier, we have data of different variants, and we actually also, the data also have a discrepancy in the sense that obtaining the hydraulic data could be more expensive than obtaining a stress strain curve. So how do we address this discrepancy of the data availability issues? And the way we propose is use a hybridized approach. The idea is actually, again, very simple. We don't actually need to use the data-driven approach for both constitutive law. We can actually choose one of them. And in this case, we can actually simplify the search problem. If you have enough data on a particular constitutive law, or if the constitutive law are too hard to generate, then we actually switch from a model-based approach to a model-free approach. If the model-based approach is actually suitable, then we will simply use the model-based approach. This is actually two additional this variance formulations of the hybridized pole mechanics formulations. In one case, the solid model is actually based on the constitutive law, but then the fluid model is based on the data. On the other case, the reverse is actually true. So this is actually the comparisons of the two approach. Obviously, a model-based approach, if it's actually calibrated correctly, would demand less data, and not only that, it can also save time. In this case, in the brute force approach, if you look at the hybridized approach, in both hybridized approach, it's actually function faster when we have more data point. So this hybridized approach, in that sense, could actually help us save some time. But another important issues we want to deal with is the discrete optimization search. So we don't have a model, but the price we pay is that in the database, we need to identify the optimum data point that help us fulfill the physical constraint. And this is actually classically done by the nearest neighborhood search. But here we will try to do something differently. So first, our approach is to try to use the KD tree search. And we basically do a simple check here. If you actually have this product norm that looks like an energy norm. Okay, so C can actually split into two parts based on the Cholesky factorizations. And in this case, we can actually rewrite the material space in and then we can minimizing it using the L2 norm instead of using an energy norm. After the factorizations, we basically would store the data using the factorized material database. And we can use the KD tree search to speed up the search. So you can think about it. If you have the brute force way to search the data point, what we basically have is that we basically need to measure the distance between the manifold, the physical constraint manifold to the particular material point. And we actually need to minimizing the distance and then rank them. So in the KD3 search, we can save a lot of time by partitioning the domain and then find out and then use the partitions to actually saving the search time to identify the point. Sorry about it. So one thing that we actually did is that we partitioned the data space into subspace and then using the KTC search to identify the particular partitions of the data. And then in the last level, we would actually just use the nearest labeled search to identify the material or the particular material data. So the result is actually, the benefit is quite obvious. So we try to do the classical brute force research. And in this case, when we increase the number of data, we actually, the model fee accuracy is increasing, but then the time is actually, the search time also increased because now we have to compare more points. Versus in the KDC search, because in each time of the partitions, we actually would only select half of the data point, we can actually have the search speed for the discrete problem actually increase much slower in a much slower way. So that could actually help us to obtain the to continue the computer simulations even when we have a lot of data point to compare. This is actually more comparisons for another problem. As you can see, the more it doesn't, whether you use the KD tree search or the brute force approach is actually doesn't matter much when we don't have enough data point. But when the data point are actually increasing, then the speed become important issues, and the KD tree search can partially help us continue the model fee simulation without suffering from a very slow constitutive update. So we compare first with the linear problem, which obviously doesn't require a model fee approach. This is just to check the model is correct, whether we use a model fee or using a fully data driven when we are given enough data point. This is actually the details of the constitutive response predictions. As you can see, one thing we can observe is that when we don't have enough data point, the constitutive response that are actually obtained tend to lack smoothness over time. This is actually simply because of the fact that when the database actually, when the point crowd in the constitutive manifold are more sparse, then the choice of the data we have is actually less. And hence you can see that artificial oscillations, which supposedly can be resolved by adding more data point. So this is actually in a sense illustrate the fact that, and this by the way is just a 1D problem. So it illustrates the fact that the model fee approach could work, but then when we don't have enough data, then we also need to deal with the fact that some of the lack of the data would actually lead to a model response that are less smooth than expected. This is actually another comparisons in the stress relaxations. So our goal is to simulate a porous media. So a porous media, when compressed, even though the solid response have no path-dependent behavior, because of the diffusions of the profluid, it will lead to stress relaxations. So here we first again generate a linear database where we simply compare and check the correctness of the implementations, and then we actually compare the algorithm. We check the algorithm whether it functions on a nonlinear model. So in this case, we use the finite element as the benchmark, and we generate the data from a model to create a point cloud, and then we actually examine the constitutive response. As you can see here, when sufficient data are available, the model can converge correctly. This is actually another simulation for the model-free approach, in which case we use a real data of a sandstone data. So as you can see here, the porosity permeability relationships are actually in a point cloud that are actually not that with very high invariance. In which case we can actually use the Cosini common to get the mid behavior, but the mid behavior doesn't necessarily capture the physics or even the train of the constitutive law. For that reason, it actually makes sense to try the model-free approach where we simply map the constitutive point into the available data point. And this is actually a fully coupled problem where we apply the displacement with no flux boundary, and we see how the pole pressure build up and how does the water moving inside the domain. In this case, we use a hybridized formulations in the sense that the solid mechanics are actually coming from a model. Only the hydraulic part are actually coming from using a data-driven approach. The reason is that the solid constitutive response, we can get a reasonable stress strain curve that doesn't have the high invariance with reasonable accuracy. In particular, from the classical triaxial compaction test data. So, and this is actually the response we will get. The domain are actually heterogeneous with porosity fluctuated in the space, and we can actually run the calculations and compute the pole pressure. So if you look at one particular constitutive, one quadrature point in the domain, what you will see here is actually that the data, as we actually run the selections, it choosing different data point on the material database instead of trying to make a predictions inside a smooth predictions. So this could make sense when we actually could not write a good constitutive law that actually able to capture all the point, or in this case, deal with the high invariance. You can see the analogs. This is actually very close to a case where the data in a neural network training where is very overfitting in a sense. We will probably get a very similar behavior. So there are some ongoing work. Actually, my student told me not to show all the steps, so I will just show the results. But here is actually the idea. If you think about it, the material constitutive response is not linear. So the tools to using to assuming that the data is actually in the Euclidean vector space is not necessarily the best approach. The reason is the notion of distance. So if you think about it, if you want to model the distance on a flat surface, it makes sense to use the norm to give us a sense of distance. But if you actually try to measure the distance on Earth, like the distance between Paris to Japan, the data itself, the surface is not a flat line. So the notion of distance, using the norm as a replacement of the distance doesn't apply. So we need to think about a different way to actually minimizing the distance by thinking about what is the manifold of the data that it lives in. So here, without all the details, but I hope that we will finish the paper by December. This is one numerical experiment, in which case we have a database, but then we actually taking out some data. Okay, and then the upper results is actually the manifold calculations. We construct a constitutive manifold and then using the correspond the right matrix to actually measure the distance and then solve the same model free problem. You can see that even in this case where there's a big hole in the database, we can get a good result versus the classical a distance search would actually lead to oscillations in the string field. This is also another ongoing work is to deal with the model free problem when we don't have enough data. Again, we can compare the two approach. In this particular case, we simply try to apply the constitutive law in on a trust system. One interesting thing we find is that when we don't have in this particular case, if we don't have enough data, even though the material is completely elastic, it's nonlinear elastic, we may actually create a seemingly path-dependent behavior just because of the due to the artificial effect of the search and also the lack of the data point. But when we actually consider the manifold approach, we may actually get a smooth response. So here, the key thing we try to convey is that we try to think about the right approach when we deal with different amount of the data. How do we switch the strategy, and also how do we measure? So one thing that in this research we find it particularly exciting is that it's not just given the amount of the data, how do we generate a model, but how do we properly measure the notion of distance? So, and then this would go to the, I think I'm a little bit running out of time, so maybe I would, how many times should I?
You're okay. We have
Okay,
20
so
minutes.
but let me know if I'm actually running out of time.
Yeah.
So
You're
the
okay
second
now.
part, so another strategy we want to talk about is working for plasticity. So at this point, we know there's some literature that dealing with model-free plasticity, but I think that right now, for the plasticity data, because the behavior is path dependent, we want to go back to something that are more model based, just to overcoming the demands of the data. So here we were actually, for the plasticity, we were actually using a neural networks strategy. So I want to talk a little bit about the history of the constitutive law. Handcrafting a constitutive law, as we all know, is a very time-consuming process. You can see in this figure, it takes almost 100 years from Mises J2 plasticity to a sand model. But then, how many 100 years do we need to wait when we have so many new material that getting designed, or meta material that are getting designed? So there's a demand on try to automate this process in some sense, and try to take advantage of the model also to improve the data collection process. So the classical approach, by classic I mean a few years ago that getting started, is to use the recurrent neural network to generate a constitutive model for the path-dependent behavior. But then there is a problem in this approach, in the sense that when we actually use the string history to predict the stress, it's really difficult to access the thermodynamics or the admissibility of the constitutive law. For example, without the spread of the elastic and plastic string, it's hard to analyzing what energy getting stored, what is the energy dissipations. So we use an alternative way where we would actually cut the whole learning process into two steps: the training of the elastic energy functional and the training of the yield surface. In particular, the training of elastic energy functional have been talked about in the literature quite often, but here our focus would be on how to train the yield surface. Okay, so in particular, if we actually just simply trying to parameterize, find out the optimum parameter of the U surface, we won't be able to discover anything new. So how do we actually retain the general, how do you make the learning problem as general as possible and not making it too difficult? That is actually one of our goals in this research. So for the lack of time, I probably would go over this a little bit faster. So the elastic part, we can actually generate an energy functional by actually the constitutive law by training the energy functional. So here the idea is that instead of training, generating a supervised learning that link the strength to the stress, we try to create a more label by actually using both the energy, the strength, the energy, the stress, and the stiffness all as an output. And we actually have this data in the experiment. We're just not using it in the classical machine learning training. The advantage of including the stiffness and the energy is that when we increase the energy, we can check the physical property of the energy. For example, we can enforce convexity. And the good thing about incorporate the stiffness is that is similar. We can also check the ellipticity and then the stability of the energy functional. So this is actually some of the response that we can get in the training of elastic energy functional. We actually found out that using a high order objective functions actually help not only on generating a better stiffness, but also on generating better stress and energy, even though the minimizations include phi term instead of just the energy term. And this method have not only applied on direct numerical simulations for the finite element. It has also been applied in our recent work on simulating HMX crystal interjecting material for finite string problem. In this case, we actually doesn't have the energy data, the hyperelastic energy data, but we actually have the stress data, and then we use the initial point of the energy to change the constitutive law for this polycrystal. We can see that even without a very sophisticated multi-layer perceptron, we can actually create a very good match in the constitutive response on the stress strain curve. But more importantly is that we can also introduce the physics through a transfer learning strategy. So here we basically try to enforce two things, the material film indifference and then the symmetry. We actually introduce a test where the rotation tensor are put into the deformation gradient, and we actually check whether we can get the same energy when we change the observer orientations. And we also check whether for the symmetry rotations, whether we can maintain the same constitutive response. And another thing that we can also do is to check the acoustic tensor behavior. So when we compute the tangents, for a given orientation n, we obtain acoustic tensor, and then the eigenvalue of the acoustic tensor gives us the wave speed of the material. In this particular case, we can actually find out what is the minimum of the wave speed, and we can actually ensure that the constitutive law actually lead to a stable result by ensuring that the wave speed is actually not going negative. I think for the sake of time, we don't have time to go through that, but I also want to say that the tuning of the hyperparameter, we also make an attempt on training it with the reinforcement learning, and we can find the optimum set of the data. So, and also for the level set training approach that we introduced, one of the important thing is that it demands the degree of continuity. So but then while we can actually choose the hypertangents activation function to enable that, what we actually found out, at least empirically, is that using the RE, LU seems to be a good choice if we can actually introduce an additional multiple layer to increase the degree of continuity. So the idea is very simple. We have ReLU activation functions. You see that corner here, if you take the derivative, you will get a jump. So it doesn't have enough continuity for us to take the second derivative to obtain the tangent. However, we can introduce a multiple layer so that the layer add itself times itself together, and that would actually increase the differentiability, and then we can actually control the degree of the continuity such that we can actually obtain a smooth tangent. So this is just some small trick. And in that particular case, this technique is applied on identifying the U surface, parameterizing the U surface. So you can think about that. The most true way to generate a constitutive law is to create a learning problem where we actually have a strain history to predict the stress. However, if we actually incorporate the plasticity framework, what we actually want to do is that if we know the elasticity, the plasticity constitutive law could be complete if we know how the U surface involved in the stress space. With that assumptions, then we can actually consider the constitutive law modeling problem as a geometry problem. We simply want to evolve a level set in the parametric space. In this case, for isotropic material, that would be just the principal stress. So with the direct numerical simulations, we can actually run simulations that are purely elastic and then compare it with the DNS that activate the plasticity portions. And from that, we can actually obtain the data that identify the plastic strain. And from that, we can constitute a U surface. So there are previous work on using the NURBS to identify the U surface for perfect plasticity. The problem is that when a material show a plastic behavior, the U surface can be evolved in any arbitrary way possible. If we actually, from a solid mechanics background, if we study J2 plasticity, we all know that the U surface can enlarge in the stress space or move in the stress space. But in general, the material, the symmetry of the U stress can also change. It can also rotate. So one of the most generalized way to represent that stress strain behavior is actually create a parametrizations of the U surface along with the cumulative plastic strain. So in this case, we were formulating the U surface revolutions as a Hamilton-Jacobi equations. You can think about this very similar to training a pin problem where we actually try to solve that Hamilton-Jacobi problem with the U surface corresponding to the principal stress and the accumulative plastic strain. The only difference here is that we only need to train this pin problem once, and this could be and then the result would be a constitutive law that can be reused many times as a replacement of the classical return constitutive law. So I think I'm about to running out of time, so I will just talk about the basic idea. We can get in this particular case, in this particular paper, we can actually obtain the U surface, and then if we continue to load the material, we can observe what is the plastic strain, and from that we can actually record the evolvement, and then substitute, and then adding the data, and then the physical and the governing law of the Hamilton-Jacobi equations, we can actually change. We can actually change U surface that are actually getting evolved with the cumulative plastic strain or any internal variable. So here, to simplify the training, again, we want to generate the constitutive law that are as smooth as possible to overcome the oscillation we may sometimes observe in the recurrent neural network. So the way to do it is the following. When we're generating the data, we would only observe the yielding point, but then this will be just a point it will be just be a surface in the parametric space. However, we can make assumptions that the U surface is assigned different functions. In this case, then we would generate a lot. We can generate as many data as we want in the principal stress space, in addition to the Hamilton-Jacobi equation to train the model. So in this particular case, with the assumption that the U surface is also assigned different functions, we can actually, the experimental data can help us capture how does the U surface evolve in time, and then the resultant constitutive law are actually in this particular case can be put into a classical return mapping algorithm. We can also use the plastic strain increment to introduce a non-associative flow rule, as this example shows. We don't necessarily need to change a plastic potential. We can, but we can also compare the rotations between the stress gradient and the plastic flow direction to generate a non-associative flow rule. This is actually the difference between simply training a U surface and assuming then the U surface is actually assigned different functions. And the implementations is actually very simple. This is also one of the attractive point of the level set plasticity model, in the sense that if you have a production code or constitutive law that already have a return mapping in the string space, you simply need to replace the classical elastic energy functional and then the U functions with the train functions. The elastic neural network train, the neural network that predict the stress response, and then the neural network that actually solve the Hamilton-Jacobi problem will be put in here and here respectively. And it can actually reproduce a lot of different plasticity model with various type of hardening. This is actually exciting because instead of handcrafting different type of constitutive model each time, we can merge all the effort into one meta model. And given different data, it can manifest different type of hardening, different type of U surface that in the history of time I actually handcraft one by one, and it's in a very time-consuming manner. So this is some response that actually we see. We actually identified something very close to a CAM-crate plasticity, but it can actually have a very complicated hardening or softening mechanism in different loading path. So we can compare this with the RNN, even with the limit data, because in this case, we don't need to use the recurrent neural network. What we actually need to do is to use the multi-layer perceptron. The training is much easier, and because we don't actually need, we would actually impose the memory through a KKT conditions rather than through the memory gate. We don't see the oscillation that could be occurred in LSTM or in the gated recurrent neural network. This is more response. As you can see, the nice thing is not only we get a more stable response, but you can clearly see that we increase the interpretability of the constitutive law. Here we know how does the U surface evolve, and that tells us something about the anisotropy evolvement of the U surface. And also we can check whether the U surface are thermodynamically admissible by simply checking whether it actually have the convexity required for a stable or physical compatible model. So we're using this to replace the classical FE square approach, in this case FFT finite element approach, in which we have a polycrystal and then we train it with the neural network and then we're replacing it with the FE square approach. As you can see, we can actually run the polycrystal simulation without actually associate each gas response with expensive FFT simulations. And not only that, we can discover a macroscopic model that actually have interesting physics in it. So this is the comparisons between the two FFT simulations with the surrogate model. As you can see, the results are reasonably close. We also think about how to expand this research. In particular, what we haven't talked about is the way to incorporate the internal variable. internal variable representation of the memory. And one of the reasons that the material demonstrate path-dependent behavior is because of the memory effect due to the particle internal rearrangement change. And this could be very effectively represented in a graph. The microstructure can be represented by a graph, and there could be a way to capture how does the graph evolving during the constitutive load, during the plasticity loading, and we can actually connect it with the physics. So in this case, instead of handcrafting a fiber tensor or porosity or whatever physical internal variable to constitute a constitutive law, we will directly generate a low-dimensional representation of the graph, and then using the revolutions of the encoded feature vector to actually incorporate into the constitutive law response. So we can see some comparison. This one is still ongoing work, and this is first benchmark against the recurrent neural network. But you can see that it can predict a pretty complicated cyclic behavior. Another thing that we have been doing is to introduce the variational plasticity in the energy with energetic approach, where we actually simply change the elastic energy functional and then the plastic energy functional. And this is actually compared again the J2 plasticity case. And also, finally, one ongoing work is not only on the upscaling of the constitutive law, but on the downscaling. So if we actually have a FE square simulations at some point, we want to actually continue the simulation not using the neural network, but directly convert it back into the microstructure. Can we do that? So in this particular case, the finite elements nodes are actually represented as a graph, and we actually find out what is the low-dimensional feature of the node wave graph evolved, and then we're using that node wave to we're actually using the low-dimensional representations of the encoded feature vector. We predict the revolution of the encoded feature vector, and then using a decoder to get back the field data. So with that, I think I already said too much, running out of time. So I will say the following. We have, in the constitutive law problem, we more or less deal with different amount of the data. What we can control is the string and the hyperparameter and then the method. But one thing I think that, at least based on my personal experience, that are very important is not necessarily finding what is the most latest gadgets or the neural network that architecture that can solve the problem, but to think about how to formulate the problem properly. And I think that in this case, I think I show a few examples where we are giving the same amount of the data, but depends on how we use those data to make a predictions, we can get a very diverse response of different quality and robustness. So with that, I want to thank all the audience for their patience to listen to my talk. I want to thank my sponsor for their continuous support. I want to thank my student again, Nick and Bahado, for working very hard on getting this thing done. And you can find more information from our research group webpage, www.promechanics.org. And thank you.
Thank you so much, Steve, for the wonderful talk. I didn't want to stop you because I hope I wanted everyone to get full material from you, although it's going over time because it's recording. People can check the recorded video next time. So that I didn't want to stop you. All right, great. Thank you so much for the great talk. Let's have a Q&A session, maybe for briefly. If you have any questions, please unmute yourself and then ask questions.
I have a quick one, if that's all right. And yeah. Your talk. So the data or the model-free, the data-driven approach, where you're looking for the closest point in your solution space. When you showed the points that were selected by a single gas point in your simulation, have you looked simulation-wide at the statistics to see if you are giving all points at a given, say, porosity even treatment, or if you tend to localize within regions of the solution space? So say, you have
So,
some statistical variability in your data set, and do you tend to overestimate the variability based on your sampling or capture it uniformly? I mean, are all the points been equally weighted, or are the ones at the surface of a cloud of points or the interior of a cloud of points tend to be weighted more heavily, for example?
so right now, so if I understand the question correctly, right now, the point doesn't have a different way, so we treat equally. But that being said, the energy norm, the C and S parameter that you choose, in a sense, also affect indirectly affecting the importance of how you perceive your perceptions of a distance. And I think there are some work from the French group, Laurent Steiner, that actually study how does the choice of the C, if he's solving a solid mechanics problem, how does it affecting the convergence. So to answer the questions, my understanding, and my student Bahadur is in the audience, he can also jump in. My understanding is that the data, how does the data distribute does matter. Here in the most example, the data is quite equally distributed. But then again, if you actually have a data that concentrate in some parametric domain and very sparse in other domain, that could cause issues if you're simulating in the region that have very sparse data.
Right.
Because even the closest point you can actually map to is still very far away from the ideal situation where you have the actual data. So I think it could be.
Well, I guess I don't mean, are you purposefully applying weights to the data points? I mean, does the algorithm tend to bias some points more than others because of whether they're in the middle or the edge of a cloud? As like if you were to sample the number of times each point was selected as the nearest point in a simulation, do you see?
I don't think so. Although strictly speaking, if you're a nonlinear constitutive response, then because you compute sort of like artificial energy from that energy norm, maybe I can show that energy thing. So because so you would actually if your material is actually nonlinear, and then your norm is actually, your C is actually constant, you do have a perception that would bias that would actually bias towards some point over the other, but it's not inherently there. This is just because of the norm. This is just because of the norm you choose. Again, if the data set obviously is linear, then every point is treated equally. You can think about it. So you can think about it. It's like if you have a curve and then you want to measure the distance. If you actually very far away, you can actually use the curve length to measure the distance, or you can use a straight line. So if you use the norm, is equivalent to use a straight line. So that would affect your perceptions. That will affect your perception a little bit. So it could be, you can think about it, it's like what is that called? In the 1D case, like a differential one form where your form is actually just a constant flow. I don't know whether I explain it properly, but yeah, yeah. And actually, Chanton may also also know what I'm talking about. So yeah.
At least when I've tried to do similar things when you have noisy data like this, is that sometimes the minimum distance formulation can preferentially select outliers. But it also depends on how you're randomly selecting your original data set. And so one of the questions that I had actually in your plot of the migration of the single integration point, if you could go to that slide, which is in the neighborhood of this, where was it? Maybe it was a little bit farther down, where you showed the actual migration that he had referred to.
The migration. So
Yeah.
this one.
Yeah. So one of the things that I noticed here is that there's kind of a direction to the migration.
Uh-huh.
And so what I was curious is this coming out of, because sometimes I've noticed that the data points will kind of equilibrate a little bit because of your constraint set. And so it depends on your data set and your initial selections, but it's believable to me that you would migrate to similar portions of the domain if everything's well conditioned. But I was curious if this is under like a linear ramping, and so it's kind of updating boundary conditions, and that's why it's pushing you in a direction, or the algorithm is itself migrating like this.
So I would say, I think that this question I probably need Bahadur. Can you answer that?
Yeah, hi. Actually, because here we had like porosity is also a feature for us. So we have like porosity, permeability, not sorry, porosity, pressure gradient, and velocity. So and for each porosity, we have a different data set. So our data set is in a sense has one more dimension than classical sense. So based on the porosity, we just choose like the closest porosity from that data. For example, if your porosity at this point of simulation is 0.2, first I decide find those closest porosity data sets and then search inside those data sets, which each one has like so many data points, right?
Yeah. So
That's the hierarchy we do in the actual simulation for this particular problem because we wanted to keep track of the porosity evolution, and our data sets are generated based on that porosity.
Okay. So the question I was asking related to the fact that you kind of seem to have there's very much a rightward trend in the data, like you kind of have a general direction. And my
Yeah,
question
that's
was,
true. Yeah, that's true. Because of if Professor Sun go back to the previous slide, you see orally the domain is like in the compression mode, right?
yep,
So because of that compression, we expect
the
to
porosity,
yeah, the reduction in the porosity, and that's why you see that trend.
okay. My question actually was, are the boundary conditions sometimes in a nonlinear problem we very often will ramp certain boundary conditions, right?
Mhm.
And I was curious if that was what that was, or if that was just merely the constraints kind of cinching in on the correct data point in that migration.
So the algorithms finds that like we don't assume how to do that. So the algorithms finds the closest data and just substitute in the equations. That's why
So over the course of that migration, your boundary conditions are constant?
in here, if I remember correctly, for this, I think I increased the boundary that displacement is increasing. So the lateral compression is fixed, but that U is increasing during the time.
Okay, so that makes sense. So basically what we're seeing, so that was kind of my internal question, is I have seen migrations of data points under fixed
Oh yeah,
boundary
definitely.
conditions.
This is a transient problem. So I
Okay.
gradually increase the compression from the top.
Okay.
Yeah. So because it's a pole
Okay.
mechanics problem, so it has multiple time step.
Well, yeah, my question was mostly whether it was at a single instant in time or whether this was over.
Over, yeah, entire simulation from the
Okay,
beginning to the end.
Yeah.
cool. And then I did have one other question about your discretization. So when you add time to your constraint equations, which is, well, we don't necessarily need the exact one. So in the past, when I've done that, I needed to make a specific numerical approximation to set up that constraint. Did you guys have to do that, or was there a different space you were able to make that constraint in?
Actually, we use the idea, so in the optimization sense, we could do first in discrete in time and then a space, or first in space and then time. So what we did is like first in time, because when I make it first in time, it would be easier for the distance minimization to do the optimization on the space. That's why you see that delta T in the norm. If Professor Sun goes back one slide.
Yeah, I think that idea also come from, I mean, on relay work. I think that Professor Ortiz, we are with also with Raul, have done some work on that equivalence. What is that called? If equivalent static thing, it discretize it in time and have discrete Lagrangian and then find the minimizer. So yeah, so if we look at the paper, we basically follow that idea just for convenience more than anything. Just to make it discrete in time in each time instant, you kind of solving a local quasi-static problem, and then we update it to the next step. Yeah, exactly.
Okay. Yeah, I didn't have. Could you go back to the equation just one more step? Or I think he said in your slides. Oh, there it is. Okay.
So the so you can see.
Yeah, that looks familiar.
Actually, one more previous. I think one slide previous than this one, and also more. Go back, please, Professor. One more, sorry. Here, you see the next one. Here, you see that delta T multiply. Next one.
This one.
Yeah. So the pyromechanics metric is the first equation below than the proposed norm for poroelasticity.
Oh, you want
that delta T is coming because of the first discretizing in time.
Yeah.
Okay. Just to make it consistent, because that one would have the unit of a power and this one would have energy.
Yep.
All right, sounds good. I think, is there any other question? I think it's a time to wrap up, by the way.
I think we're 15 minutes past wrap up.
I know, exactly. All right, but that's good. I mean, that's good. There are many interested in the Professor Sun's work presented today.
Yeah, very interesting.
Yeah, wonderful. All right, I guess with that we can conclude the seminar. Let's thank our speaker, the Steve Sun.
Thank you so much.
Great talk, and hopefully, this becomes a chance to do the future collaboration with.
Yeah, I hope so. Yeah, I may one day visit Lawrence soon. So.
Yeah, I mean, don't just do the collaboration with the Sandia. Please collaborate with Lawrence Livermore too. Okay. We are jealous. All right. Thank you.
Thank you so much.
Thank you, Steve. Okay, let's end the meeting today. Thank you, everyone, for joining.
Thank you. Bye.
Thank you.